In 1875, Charles Eliot had a difficult decision to make. The president of Harvard University and cousin of the acclaimed poet T.S. Eliot had a position to fill. 2 years earlier, the Kentucky-born mathematician Joseph Winlock had died unexpectedly after having served as the director of the Harvard College Observatory for nearly a decade. A gifted astronomer and one of the founding members of the United States' National Academy of Sciences, Winlock had conducted solid research in making the typical sort of astronomical measurements one might expect of the position and motions of heavenly objects, while also in making improvements to the observatory's equipment and facilities. However, while the observatory was one of the preeminent observational facilities of the time in the Americas, it lagged behind its European counterparts in London, Paris, and Berlin. For Eliot, always the innovator in higher education, this was bothersome. While it was rare to have an academic observatory at the cutting edge of astronomical research at this time, as most such facilities were funded through either government grants in order to improve mapping or navigation, or created by private individuals, Eliot had something a bit different in mind. He wondered if he couldn't break the mold just a bit and create a cutting-edge facility that would do work outside the traditional purview of those other types of institutions. To do this, however, he needed the right person to lead the team of astronomers and assistants that worked at Harvard's observatory, performing various tasks that had been established by Winlock. For 2 years, Eliot would deliberate on the choice, seeking counsel where he could find it, asking what directions research in the field of astronomy and astrophysics was headed. In due time, he began to formulate an idea. Positional astronomy, what would soon become known as astrometry, was a field already well covered and increasingly well understood. This was about as far from cutting-edge research at that time as could be imagined. It was solid, proper, and completely unremarkable work. On the other hand, Eliot had come to learn that there were new developments both in the study of the light being gathered by increasingly large and complex telescopes, and in the ways of recording that information. Stellar spectroscopy and astrophotography, while still relatively new, offered up a chance to do important and potentially groundbreaking work. Astutely, Eliot recognized that as these lines of inquiry were outside the traditional boundaries of astronomy, he might need to find a director that was something of an outsider as well. But he knew that the person could only be an outsider in terms of disciplinary boundaries. As the observatory's research was funded mostly through external sources, with only the salaries for the director and a few staff positions coming from Harvard itself, the person selected would have to be able to raise money for any new projects to be undertaken. He would have to know Harvard and Boston and how to convince the wealthy to hand over their money for unlocking the secrets of the universe. As he worked through the credentials of those who indicated interest in the position, he found a lot of astronomers who could reliably carry on the work of the observatory. But, in time, another name floated to the top of the list. Edward Charles Pickering was a Harvard man, as they say. He attended the Boston Latin School and then received his Bachelor's of Science from Harvard before traveling the short distance to the recently established Massachusetts Institute of Technology to teach physics. He understood spectra and optics and might bring with him a new perspective on research to be done. However, when Eliot began privately discussing the possibility of hiring Pickering with those around him, he encountered a good deal of pushback. Hire an astronomer, he was told. There were many excellent names on the list. Yet, he persisted in his belief that the observatory could do more than it had been doing, and eventually prevailed in his desire to appoint Pickering. In 1879, the Bostonian was hired. In his perseverance, Eliot would prove to be truly visionary, as would be the case with many of his other initiatives. Not only would Pickering institute new research programs, he would be more gifted than even Eliot could have hoped for in drumming up financial support for even more ambitious projects that would extend the observatory's work to South America and produce an astronomical legacy that still gives insight even today. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 34, The Harvard College Observatory. As we begin, I should start off by saying that this episode is something of a hybrid. Usually when I do a show focused on a single person or institution, I tend to try to think of it as something that somebody, a listener, could pass by if they wanted and still keep track of the main narrative, and so I call that a supplement to the show. However, as we look at the specific work of the researchers at the Harvard College Observatory, what we will find is that this work is so foundational to much of what we'll be talking about going forward that I've decided to leave this episode and the one that follows it in the main narrative. However, you as the listener should understand that there will be a higher amount of biographical material in this show than I usually include in that primary narrative thread. This will be balanced, however, by more technical information than I usually include in supplemental shows, and pieces and parts where I spend some time trying to explain why a given piece of scientific work is important. As I look at the landscape from a very high altitude, it's hard to imagine having the modern cosmological view were it not for the work done in Cambridge, Massachusetts, under first Edward Charles Pickering and later by his successor, Harlow Shapley. While men such as George Ellery Hale, George Humason, and Edwin Hubble in the United States, and Albert Einstein in Germany and Arthur Eddington in Great Britain will be vital to putting together the puzzle pieces, it can be safely said that without the work of an amazing group of women employed at Harvard, our modern understanding of the cosmos would have been delayed at least by decades. So, to move forward, let's take a bit of a step back to spend just a little more time looking at Edward Charles Pickering's life, as there are a number of things that we'll see in it that will be important going forward. As was the case with Lewis Rutherford in our last episode, the Pickering family stories went all the way back to the earliest days of the founding of the American Republic, with his first ancestors arriving in Salem, Massachusetts in 1636 from Yorkshire, England. His great-grandfather served in the cabinets of both Washington and John Adams, and so it could be said that Edward came from about the oldest money Boston had to offer. He attended a private grammar school as a child and then went to the Boston Latin School, as was customary of young men of his social standing. To say that he hated it would be something of an understatement. He had little use for memorizing long passages of classical literature, but in the curriculum there was just enough math to capture his imagination, and when it came time for him to pursue higher education, it didn't take a whole lot for Charles William Eliot, then assistant professor of chemistry at Harvard's Lawrence Scientific School, to talk him into enrolling there in 1862 at the age of 16. 3 years later, Pickering would graduate from Harvard with his Bachelor of Science and stay on for another 2 or so years as something of a teaching assistant before moving to take the physics position at MIT. He spent 9 years at MIT, and it was here that he really showed off his penchant for re-examining old ways of doing things and reforming outdated practices and institutions. At the time, most physics instruction consisted of placing students in large lecture halls and making them listen to lectures and watch the professor demonstrate various physical phenomena with very little hands-on work. Pickering revised the curriculum at MIT to include mandatory laboratories for the first time that included the requirement that students not only use the equipment, but also that they come up with their own novel experiments, usually centered on examining the various phases of matter. And it's there that we find him really focusing on helping people get a feel for how original research was done. To facilitate this, he wrote all of his own experiments and would eventually publish them as part of the first laboratory manual ever produced, something titled Elements of Physical Manipulation. I think it was 2 volumes long. For all of you out there of a more theoretical bent who wish that they hadn't had to do lab work while you were in college, you can thank Pickering for the inclusion of that material in your degree programs. Now, this is where Charles William Eliot enters the picture again. Eliot had risen from being a lowly assistant professor of chemistry and mathematics at Harvard to the position of the university's president through a combination of extraordinary hard work and vision for the university as something more than a regional theological school. He saw Harvard as being able to educate a person in the classical, liberal tradition of human flourishing, and so he had begun to remake the institution in that image. In the years since he had first recruited Pickering as a 16-year-old freshman, he had kept in touch, and when the observatory that served Harvard's undergraduate mission needed a new research director, he began to reach out. As I mentioned in the intro, there was a good deal of opposition to Eliot's plan, and so he proceeded actually in 2 steps. First, he hired Pickering as a professor of astronomy in 1876 to show the faculty that the fairly young man was a capable teacher and researcher. Then, a year later, with the faculty behind him, he named Pickering director of the observatory in hopes that he would do with it the same sorts of things he had done at MIT. Pickering's background in physics meant that he was willing to push the observatory's research programs away from the path they had long followed under Winlock and the directors before him. While he certainly didn't want to leave astronomy behind, he had an intuition that the emerging subdiscipline of astrophysics was where the next great discoveries were going to be made. Fortunately, the observatory had an excellent instrument for Pickering to build on. The 15-inch Great Refractor, as it was known, had been installed at the observatory by its first director, William Crouch Bond. Until recently, the telescope had been the largest in the United States, and it was an exceptionally high-quality instrument, having been used by Bond and then his son, who followed him as director, to discover Saturn's moon Hyperion and Saturn's innermost ring, known at the time as the Crepe Ring. Pickering's first goal was to begin to establish a catalog of records that documented stellar brightness for as many stars as could be observed from Harvard. To do this, he made 2 really important decisions. The first was to adopt the visual magnitude system that had first been developed by Hipparchus, but, importantly, had recently been modernized and mathematized by Norman Pogson in 1852. The scale adopted Hipparchus's 1 through 6 magnitude scale, but was based on Pogson's realization that the human eye measures brightness on an increasing logarithmic scale rather than on a linear one. What Pogson deduced was that each higher magnitude star was actually about 2.5 times brighter than the next lowest magnitude. And here's where things can get a little confusing. When Hipparchus came up with his magnitude scale, it was really more like a ranking, with the brightest stars ranked with a 1. We're number 1. We're number 1. And the dimmest being ranked number 6. Since Pogson kept this order, a magnitude 5 star is said to be about 2.5 times brighter than a magnitude 6 star. A magnitude 4 star is 2.5 times brighter than a 5, or about 6.25 times brighter than a 6, and so on. What this means is that a magnitude 1 star is about 100 times brighter than a magnitude 6 star. This is known as the apparent magnitude of a star, because it is the magnitude that the earthbound observer sees. As we will discuss, there are a number of things that can affect this, and as such, this number, without an accompanying distance, is really of only limited usefulness. The second decision Pickering made was to select one and only one star to compare all of his other observations to. The star he selected was Polaris, or in astronomical terms, Alpha Ursa Minoris, the brightest star in the Little Bear, as it was. The reason for this was that the star was always on the meridian line running from north to south, and it was thought, at least at the time, not to change in brightness, something we know isn't quite true anymore. So, to give you a sense of his idea, what he wanted to do was compare the brightness of every other star he could see to the North Star, which, by the way, he assigned a Pogson magnitude of 2.12. Tonight, if you get the chance, go out somewhere dark and use the Big Dipper's 2 pointer stars at the end of the bowl to find Polaris, and then imagine trying to compare the brightness of every other star in the sky that you can see to that in order to come up with a magnitude number for each of those stars. Now that's a pretty daunting task, especially if you have to deal with all of the other stars vying for your attention, and you have to look in one part of the sky and then back to Polaris and then back to the first part of the sky, etc., and so forth. So Pickering came up with a better plan. He went to the instrument manufacturer Allen Clark & Sons and asked them to build him a special eyepiece attachment for the great reflector, something he would call a meridian photometer. Well, I've not been able to find any really good diagrams of how the apparatus works specifically. What it did by using a series of mirrors and prisms was to bring an image of Polaris into the eyepiece of the telescope alongside of the specific star the observer wanted to estimate the magnitude of. While this would only work if the star being observed was on the meridian line, it did allow for direct comparison between that star and Polaris. What this meant was that an astronomer taking data would be able to swivel the great reflector up and down to point at different altitudes on the meridian line and also still be able to look at Polaris. If he, or as we shall soon see, she, wanted to observe a specific star, it would have to be observed in the short time window of just a couple of minutes while it was along the meridian line there. As such, detailed observing schedules would have to be created to make sure that the telescope could be used to see as many stars as possible in a given night. In this way, stars could be observed over and over and over again over the course of many nights to see if their brightness had changed. This, as you might imagine, was profoundly tedious work once the kinks got worked out. But Pickering was never one to shirk his place at the eyepiece, and it's estimated that he made over 1.5 million observations of stellar magnitude over the course of his quarter century at the observatory. All told, by 1908, the effort would result in magnitude measurements of over 45,000 stars that would become the standard reference for astronomers and astrophysicists around the world. It would also establish data on the changes in the brightness of variable stars that would prove immensely valuable later on. Pickering wasn't the kind of director who managed from a desk and expected a staff to carry out his research program. He was at the telescope night after night as much as his responsibilities allowed. It was a monumental effort that would set the example for everyone who worked around him. As the research at the observatory began to pick up, more and more data was being produced, and of course, there were more observing schedules to compile. The data had to be compared, cataloged, and archived, and all of that took time. It wasn't, however, particularly difficult work. One didn't necessarily have to be a long-term trained and skilled astronomer, but rather, what was needed is someone who was meticulous and good with numbers. As such, Pickering continued the practice of hiring what were known as human calculators, or just calculators for short, to reduce the information to publishable format that would then be released through the annals of the Harvard College Observatory. However, finding suitable people for the work was something of a challenge. For some men, often expected to be breadwinners for their families, the pay was really too low for them to take the positions. For others, they felt working at what seemed to be little more than a clerical assistant position was below their station or their abilities. Therefore, highly qualified candidates were hard to attract. This usually left students of the university to fill the positions, and they often weren't really up to Pickering's standards, especially as many of Harvard's students were now attending the university for the social advantages a degree imparted rather than for their particular self-improvement or some grand ideal of discovering new things. One day, in a peak of irritation, it is said that Pickering went off on one of his student assistants' shoddy work. Those of you who have had to supervise student work can probably empathize with his frustration, with an effort half given and hastily done as the student wanted to rush off to something infinitely more interesting than compiling numbers in seemingly endless tables to earn a paycheck they probably didn't really need anyway. In any case, the director is said to have claimed that his housekeeper could do a better job than his present assistants, and perhaps to prove a point, he brought her in and trained her to do the work. And it was in this way that Pickering set the observatory and all of astronomy down a path that no one, even he, could have foreseen. Pickering's housemaid was a woman by the name of Williamina Fleming, or Mina as she liked to be called by those close to her. She had been born in Dundee, Scotland, and in 1877 had married a man by the name of James Orr Fleming. After a year or two of school teaching, the couple immigrated to the United States, wherein her husband abandoned her and their infant daughter. When this occurred, she was forced to take a job to support herself and her child and wound up in the employ of the Pickerings as their housekeeper. She was meticulous and diligent in her work, and as Pickering and his wife got to know her a bit, they realized that she really was a woman of rare talent. In 1881, Pickering decided to hire her on as a computer at the observatory for what was going to be a new research project he was beginning. At this point, the director really wasn't all that new anymore, and he had found his footing both in the university and in the broader community of elite Boston. As was the case at almost all observatories of the time, all funding had to be raised from external sources. Some of this might come from renting out telescope time, while other monies might be raised by selling services such as precise timekeeping to telegraph or train companies. While this certainly supported a meager research program, it wouldn't be enough for what Pickering had in mind. To raise the funds he would need, he turned to his fairly broad network of social connections and began soliciting pledges of support, eventually getting some 70 or so folks to commit to giving $5,000 per year for the next 5 years. This $350,000 per year would pay the salaries of the needed staff and assistants and for the equipment and supplies, not only for the photometry work that was being undertaken, but also for 2 new projects Pickering had in mind. The first of these was what was known as a All-Sky Survey. What he began researching was how to take good photographs of fairly large chunks of the sky through a telescope. This wasn't really a simple thing to do at the time. It would take Pickering and his staff a few years to get all the procedural details worked out. Once they did, however, Pickering would begin a program of regularly photographing the entire sky in 10 degree by 10 degree sections over and over and over again onto glass photographic plates that were a little smaller than the size of a standard sheet of paper today. The reason he wanted to do this was to create a series of pictures of each region of the sky so that future astronomers could determine what might have changed in each section, even decades after the photographs had been taken. This was an act of great foresight that still actually pays dividends in modern research today, when a new object is spotted and an astronomer can go back to the now digitized photographic plates taken during this time and following in order to see what was in that part of the sky going back 100 years. The other project that was undertaken was to photograph the spectra of stars. As we mentioned in the previous episode, in the United States, there had only been one individual who had done this with any real level of success, Henry Draper. At about this same time, William Huggins and his wife Margaret were undertaking their first research in photographing spectra as well. What Pickering did, though, was something a bit different. By placing a prism at the focus of an 8-inch telescope with a shorter focal length, and then taking a photograph of the image that prism produced, he could get spectra of several stars at once. These spectra, however, were small in size and would take a good bit of care to examine. And this is where Mina Fleming became very, very important. What you need to sort of imagine in your mind's eye here is something like a thin plate of glass, maybe something like a window pane, that's about 8 by 10 inches inside. On that glass plate would be a thin chemical film that had been exposed to the light that had been collected by the 8-inch Baca reflector and then directed through that prism. This would create a negative image where the light would darken the chemical film on the plate, and each star's light in the field of view would be spread out, creating something like a grayscale spectrum. Each of these spectra would have the characteristic absorption lines now seen as gaps in the darker exposed portion of the plates. These spectra might only be a couple of centimeters long and thus would require close examination by a human being with a magnifier to tease out the spectral characteristics displayed, meaning the position and strength of the main absorption lines. Williamina Fleming was perfect for this kind of work. In 1885, as the project was beginning to ramp up, she was given the task of overseeing the classification of the spectra of those stars imaged in this way. The method generally used to do the analysis was to have the plate propped up on a special stand that would allow one person to examine and measure the spectrum of the star, while another would record the data that person spoke in some predetermined fashion. In this way, a pair of human calculators could work through each of the stars and their spectra on the plate in turn. The original plan for the research project was to record as many stellar spectra into Secchi's classification scheme as possible in order to create a much larger dataset. However, as is often the case in science, when limited data sets are expanded, the early organizational systems created to group that data usually also have to be expanded. Now, to be clear, this project, as Pickering conceived it, was a huge undertaking. To be able to realize his ambitions, he would need a lot more resources than he had available. Recall that he now had 3 ambitious projects, plus the usual astronomical work of the observatory, all going on at once on the 3 or so telescopes at his disposal. The photometry survey, the All-Sky Photographic Survey, and now that Stellar Spectra Survey. Each of these vied for telescope time, dedicated observers and astrophotographers at night, and assistants to work with the data during the day. Most importantly, it all cost money. Lots and lots of money. This is the point where a tragedy was turned into a memorial. In 1885, as Pickering was launching his 3rd new research program, he was also hoping to help an old friend, the widow Anna Draper. Anna Draper had been the wife of the noted physician and amateur astronomer Henry Draper, whom we've mentioned a couple of times in these last 2 episodes. Henry's father had been the first to take a photograph of the moon, and Henry had been the first to get a photograph of a stellar spectrum, that of the star Vega, that had enough resolution to clearly show the star's absorption lines. The Drapers had wed in 1867, and in 1873, just a year after photographing that stellar spectrum, Henry had resigned his position as Dean of Medicine at New York University in order to pursue his ambition of doing astronomical research, an ambition Anna both supported and wholeheartedly participated in. Over the course of the next several years, the two were engaged in a number of astronomical observing missions, and Henry began the process of constructing a very high-quality private observatory on his estate known as Hastings-on-Hudson. In 1880, he took the first photograph of the Orion Nebula and obtained the first photographic spectrum of Jupiter. All of these plans, though, were cut short by Henry's untimely death in 1882 of what was likely a viral infection that led to double pleurisy, or a swelling of the linings of both lungs. While devastated by the loss, Anna pledged to carry on her husband's astronomical legacy, but it soon became apparent that first settling her husband's estate and then running her own left little time for her to master the techniques she had previously assisted in. Edward Pickering and his wife had been good friends with the Drapers, in part out of shared professional interests, in part out of shared social standing, but for the most bit, really out of genuine affection. Henry's death also hit the Pickerings hard, and Edward had offered Anna any assistance she might need. Initially, this had been an offer of both personal condolence and professional courtesy, with the latter coming in the form of advice on how to proceed with the private observatory and things surrounding it. However, as issues on that front began to become overwhelming, Edward offered Anna another path by which to memorialize her husband and his scientific contributions. Why not take a bit more time getting things in order at the observatory, and instead of trying to get it all going right now, endow the spectroscopic research program that Pickering had in mind in her husband's name? While it took a bit of time to convince her, Pickering eventually won Anna over to the idea, and the Henry Draper Memorial Fund was endowed in 1886. Anna's generous gifts set an example for other notable philanthropists who also donated large sums to the burgeoning research being done at the observatory. Very quickly, Pickering had all the money he needed to begin the work in earnest, and the person he chose to oversee the bulk of that effort was Williamina Fleming, who was given the authority to hire and train all of the calculators for the project. Now, at this point, I'd like to leave aside, for the time being, this revolutionary step Pickering and Fleming took in hiring a number of very highly trained women to be part of this and the other projects of the observatory, as I plan to cover that in our next episode. This week, I'd really like to focus on some of the more technical aspects of what was being done to give you all an insight into just how the research went and just how tricky it was for astrophysics as a discipline to go from stars have spectral lines to the complex model of stellar evolution we have now. What's really going to happen, the real focus of this project, is one of these Francis Bacon natural history kinds of things. If you will recall, Bacon's method of doing science, something sometimes known as eliminative induction, was to gather as many different types of instances of some natural phenomenon, say things that give off light or types of birds or whatever, and then attempt to group those things that are associated with that phenomenon based on characteristics they either share or lack. In the case of light, for example, maybe there are things that produce both heat and light, while others only produce light. Then there are the things that actually emit light, while others merely reflect it without producing their own. You can probably think of a dozen different ways to group different light-associated things and properties. Now, what Bacon thought was that by grouping things according to both their similarities and their differences, a scientist could uncover the underlying relationships between those things. And this is where having an organizing principle can be really, really helpful. In the case of birds, you can classify a bird by observing certain things about it. Its size, the shape of its body, the shape of its wings, its coloring, the shape and size of its beak, etc. Bird watchers do this sort of thing all the time. They observe a bird in the wild, and having some training, they know exactly what to look for and are usually able to distinguish pretty quickly between, say, a particular type of finch and a chickadee. However, to be able to do this, someone, a naturalist or a natural historian of the botanist variety, had to do a lot of observing and capturing and measuring and such to determine the various different species of birds in a given area. Many different birds had to be captured and measured, each being compared with those caught previously to see if they were a new thing that hadn't been examined before, or if they already belonged to some existing classification. The more birds that were caught and examined, the better and more comprehensive the classification scheme for birds got. So let's apply this in the case of stellar spectra. Starting with Angelo Secchi, this is what first astronomers and then astrophysicists started to do. They were really capturing different stellar spectra and comparing them to other stellar spectra to see how they were alike and how they were different. Now, added to this is the wrinkle that the astronomers and physicists know that different spectral absorption lines are created by different elements, which have only just begun to be organized in various ways, with the table of Mendeleev and Meyer becoming the most widely accepted in the 1870s. You know, that periodic table thing that we talked about in the second season of the show. There was also the question of why one star's spectrum might have strong spectral lines at some of Fraunhofer's most notable places, while other stars had strong features in different places, but didn't have features in the places the first stars did. To this, then, was added the idea that different stars have different overall colors, from bluish through white to yellow, orange, and then red. While certainly not as complex as our birds example, astrophysicists were hampered by the fact that they couldn't actually capture their stars and examine them in great detail. It was going to make for a really interesting puzzle, and it's one that we're going to have to unravel over the next few episodes. So let's start by taking a moment to review Secchi's work, as it really formed the basis for all subsequent efforts. As you will recall, Secchi eventually had 5 different classes of stellar spectra, though it's really the first 3 that contained most of his first observed stars. He'd done much of the classification based on which spectral lines were present and what they looked like. It was really a pretty simple scheme, but it was a good place to start. All of the stars in his class 1 had really broad Fraunhofer F lines in the blue part of the spectrum, along with additional broad lines in the violet and far violet regions. His type 2 stars had spectra with a number of fine absorption lines throughout the spectrum at most of the Fraunhofer points, while class 3 had broad absorption lines throughout the spectrum. His 4th type of spectrum, something he discovered after his initial papers were published, actually looked somewhat similar to his class 3 stars, with the exception that they also showed bright emission lines in the red part of the spectrum just to the side of an associated absorption band. These were called carbon stars, as the emission lines matched up with the spectrum of carbon. And by the way here, just a really quick note. One of the things I may do here is that, like I said, I might get a little bit technical in sort of talking about these various lines. So just to review quickly. When Fraunhofer had observed the spectrum of the sun, what he had done is he had marked off about 8 or 10 absorption lines that he thought were particularly important. He gave them various letters, A, B, C, D, etc. When spectral classification is going to take place, those are the lines that everybody's going to be comparing the spectra of their stars and the absorption lines in those spectra to. So if I ever sort of get going on this and you're sort of wondering what the comparison is, it's almost always going to be back to that original Fraunhofer spectrum of the sun. Okay, now let's return to our natural history approach. If you were to look at a spectrum of an unstudied star, you would examine its spectral lines, and if it had the broad lines in the blue and violet parts of the spectrum, you'd call it a class 1 star. A bit like if you were a bird watcher and you spotted a small bird with certain types of features, you'd call it a finch. At the point of Secchi's work, you probably couldn't do much more than that, as his classification scheme, as we've said, was pretty basic. However, added to this was the work of Huggins, who was looking at spectra of very bright stars superimposed with emission spectra created by sparking various elements. What Huggins and others were able to do was begin identifying certain spectral features with various elements, most notably hydrogen. Now, of course, this raises the question as to why hydrogen absorption lines show up in some stars and not in others, or showed up more strongly in some stars and less strongly in others. The final piece leading up to the work at Harvard was Vogel's work in Germany. He had somewhat better instrumentation than Secchi had had, and so his spectra showed a bit more detail. As such, he came up with his own classification scheme that was notable in that it subdivided Secchi's class 2 stars into 3 subcategories based on spectral line differences. Much of his work would take place concurrently with the research program undertaken by Pickering and Fleming. So, with the generosity of Anna Draper, the Harvard group now had the resources to take a lot of pictures of the parts of the sky and capture the spectra of a lot of stars. At this point, both the technology and the methodology of the American team was somewhat ahead of their European counterparts, even as the optics for their instruments usually had to be ordered from French or German manufacturers. In particular, Pickering had built on the work of Louis Rutherford and Henry Draper in photography and thus could record very precise spectra with clearly delineated spectral lines, even if his calculators had to use a magnifying glass to distinguish those features. Over the course of the next 4 years, the Draper Memorial Project, as it was known, collected and classified the spectra of some 10,351 stars in the part of the celestial sphere from about 10 degrees below the celestial equator up to the celestial North Pole. All of the classification work was done by a team overseen by Williamina Fleming, and as part of her work, she was given free rein to establish whatever sort of classification scheme she saw fit. What she came up with was on the other extreme of Secchi's simplicity. Where he had a very simple, limited classification system, she had 16 different classifications based in large part on the strength of the hydrogen lines in the spectrum. These different spectral classes were designated by letters of the alphabet from A through O, with J omitted and P added to designate planetary nebula. Published in 1890, the Draper Memorial Catalogue was a huge step forward in stellar classification, but it also made things a whole lot more complicated. Secchi's Class 1 stars were now broken into 4 subcategories, letters A through D. Class 2 were spread out through no fewer than 7 new distinctions, while his Class 3 and 4 categories were just renamed M and N. When Pickering published the results of the catalog, he was the paper's author, but in an acknowledgement that would open the way for her to publish her own work down the line, he mentioned that the classification scheme was due to the efforts of Fleming. We'll get into this in greater detail in our next episode. As a final note, it was during this time that the observatory's director began to recognize that to truly get comprehensive data, it would be necessary to establish an observatory in the southern hemisphere. More than that, however, he began to also recognize that the encroaching light pollution of Boston and the difficulty caused by observing at low altitudes would require a site far from a major city at some altitude to afford for better seeing conditions. In 1889, with the funding he received following Anna Draper's initial endowment, he set up the Boyden Station of the observatory at Arequipa, Peru, with 2 very fine instruments. While the operation would get off to a somewhat rocky start, not in small part due to the mismanagement of Pickering's older brother William, it would in time begin sending crates full of photographic plates produced in the same way as those in Cambridge were for those extended research programs that were to come. Even though we've just begun to scratch the surface of the work done at the Harvard College Observatory, this is probably a good point to break the narrative. Pickering has established a robust set of research initiatives that he and others can build upon, and Williamina Fleming has established a method of reducing data that will lead to foundational results over the course of the next 30 years, even as the facilities of the observatory are superseded by those of other institutions. As we wrap up, let me give my now customary shout out to all of those listeners in the area of Southern Oregon who tune in and week out to share in the voyage. And if you will forgive me a personal note, I'd like to give a warm and heartfelt congratulations to one of my oldest friends who listens to the show. Tom Sweeney was a high school buddy of mine who chose to go into law enforcement after graduation. For some 30 plus years, he served the city of Medford, Oregon as a law enforcement officer, as well as working with and teaching at the Oregon State Police Academy as a training officer. This week, he's retiring after a long and distinguished career to spend more time with his wife Jamie and their kids. Tom, I wish you all the best, buddy, and thanks for being such a huge fan of the show. Whatever your next steps are, I know you'll take them with the character and kindness you've displayed over these last 30 years. Also, for those who are following us on the Facebook page, you know that I've recently been given a chance to attend a mission briefing for a NASA meteorological satellite known as JPSS-1, which is set to launch in the near future as part of a multi-part initiative to make more measurements of the Earth's atmosphere. The JPSS satellites are what are known as polar orbiting satellites, which means that they're in relatively low orbits that circle the Earth by going over the poles and then along the meridian lines in a sense. As they do this, the Earth rotates underneath them, allowing them to take detailed data of a strip of the atmosphere from pole to pole twice a day. This data will help improve the accuracy of weather forecasting, especially in predicting when and where severe weather will occur. As part of my visit, I'll be bringing you up-to-date information about the briefing and the missions, both through my Twitter feed, @ChadDavies, and at the Facebook page. Please feel free to follow both. Also, I'll try to do an episode of the podcast specifically devoted to the science and objectives related to the mission and how something like this goes through the planning and implementation stages. The NASA social gathering is on June 19th, so be on the lookout for more information soon. Also, if you haven't already done so, be sure to subscribe to the podcast on whatever service you like to use so that you don't miss that show when it's released. And if you're enjoying the voyage, please take a moment to leave us a strong review. If you know someone who you think would like the show, be sure to let them know about what you found here. We're always looking for a few more inquirers to join us on the adventure. Finally, as always, our music comes from the good folks over at the Blue Dot Sessions. If you're enjoying what you're hearing here, head on over to their newly designed website, www.sessions.blue, and check out their other compositions. We feature only a small part of their catalog, and so if you're looking for something with a bit of a different feel, you can go over there and search on a whole variety of different attributes, and I'm sure you'll be able to find just exactly the piece you're looking for. Next week, we'll dig even deeper into the operating environment of the Harvard College Observatory as the work there really begins to take off. What we'll find is a group of remarkable women who show the scientific world that they're just as capable of unraveling the mysteries of the cosmos as the men are. Until then, full sails on your journey.